Hey, and welcome to the short talk on attention sampling graph convolutional networks on BayLearn 2020. This is the abstract has been submitted both by Alexander Levine and me. Just to give you a very short introduction, let me hit the play button. Just to talk shortly about what we've been doing in a more abstract manner is we've been looking at graphs and graph structures and how they relate to graph network complexity, which is a very interesting area, because in a lot of cases actually we don't naturally have graphs, but we're embedding data into graphs. So we have to make decisions of how on the nodes as well as the edges. But interestingly, what we've been looking at so far is also how many nodes do we connect, and how does it affect like the overall accuracy values. And for example, if you have an image, we've been working a lot with image input. You could just say, hey, I want to connect the left pixel to the right pixel, then you would kind of end up with a kind of list of pixels in that sense, or nodes. And in that kind of setup, like the information propagation would be relatively slow, so you would require a lot of convolutions to expand all of the information, but it would be relatively not expensive. So each of the convolution would have very low expense, right? Because you only do like one, you only have one or two neighbors. But then if you change that and you say, oh, for every node I want to have each of the 3x3 neighbors that I would normally have in an image connected, then you end up with like a structure that is much more easy to access, and information can actually progress much faster, but still the complexity is relatively bounded, right? So you have an exact amount of like 8 neighbors per node. But what often is actually looked at instead is like a network where every node is connected to every other node. So the information passes by very, very fast, but you will get a lot of information at once, so you will need to be able to deal with that. And the questions that you should ask at that point in time is like, where's the right trade-off between all of those three options? Where's the right trade-off between the number of edges and the connection of nodes, the information flow, and also the memory requirements that you have? So for our experiments on the superpixel MNIST dataset, we've been checking on how the prediction of the digits actually changes with like different subsampling of graphs. So we have been subsampling the edges based on distance values. So we have been removing edges that have like where the nodes have like a longer distance to each other, and we have been seeing that actually if we downsample both training and testing data set, then the overall loss in accuracy is not that high. But if we only downsample the training data set and want to test on the full data set, then it becomes relatively hard. So then the accuracy values are very much different. So in full accuracy we had like 96%, right? And if we downsample for a distance of 15 corresponds to a pixel value, then we would get still 95% accuracy on the downsampled graph, but we would only get 69 on the full graph. And just to give you a better idea of where we've been actually applying this on very, very large graphs. So we've been working on histopathology images that have a resolution of 5 times 7K. Each of those have maybe around 200,000 cells. Each of those cells represents a node in the graph, and obviously we're not keen on looking onto a graph that connects every node to the other node, right? So, and if we do that, how can we downsample? So those are those interesting questions. And then the interesting part of this is actually that we don't only want to see some kind of like local properties, we need some kind of global properties as well, because of the tissues that are extracted from the samples and of the colon area. There would be different types of layers, different types of structure per layer, and we don't want to conclude that each of the layer corresponds actually to a cancer grade, But for each of the layers, we want to know what is the low level cancer grade, how does it look like, what is a high level cancer grade, and what does it mean to have no cancer, and how does it look like. And especially because in some of the layers you will have glands, so that you can see them at the lower images here on the presentation. When you have those glands, you have structures where you have like ellipsoids that are actually empty on the inside, so you have no cells, and you have the cells gathering around it, and you will need to analyze the behavior of those cells, which is very complex. And it's very interesting. So if you're interested more into that application, please feel free to look us up on arXiv. Other than that, I want to thank you for listening today and see you next year.